Hey guys, tonight we start with something simple. You press your hand against the table. It feels solid. You feel supported. The table doesn't collapse, and your hand doesn't pass through. The sensation seems so real, so certain, that you never question it. But tonight, we will. Because here's the strange part. By the best understanding of modern physics, you didn't actually touch the table at all. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And while you're here, let me know in the comments where you're listening from, and what time it is where you are. I love seeing how far this sleepy science travels. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Let's start with your hand. Beneath the skin, beneath the cells, beneath the proteins and molecules, there are atoms. Every part of your body is made of atoms. So is the table. Billions and billions of them. But those atoms are not packed tightly like bricks. They are more like distant dances, held together by invisible rules. And those dances never quite meet. Atoms, as we know them, are mostly empty. At the center of each is a nucleus, a tiny, dense core made of protons and neutrons. Around that nucleus swirls a cloud of electrons. It's not like planets orbiting a sun. It's fuzzier than that. The electrons don't have fixed paths. They exist in a probability cloud, regions where they are likely to be, but never pinned down precisely. Here's the thing. If the nucleus of an atom were the size of a grain of rice, the electron cloud would be the size of a football stadium. The rest, almost all of it, is empty space. So, when your hand moves toward the table, what's actually moving are the outermost electrons of your skin's atoms. And what they are approaching are the outermost electrons of the table's atoms. But electrons don't like to share space. They carry a negative electrical charge, and like charges repel. When your electrons get close to the table's electrons, the two sets push against each other, like two invisible cushions made of force. That's when your nerves fire. They don't wait for the atoms to collide, because they never will. They simply interpret the growing repulsion, that microscopic pushback, as contact. It feels like pressure. It feels like support. It even feels like warmth or texture. But none of those feelings come from actual physical contact between atoms. They come from the electric repulsion between clouds of particles that never really meet. You've never truly touched anything. Not once. And you never will. This idea isn't some fringe theory either. It's physics 101. But it runs so deeply against your daily experience that your mind doesn't want to accept it. You hold a coffee cup, high-five a friend, or fall onto your bed, and it feels real. But it's not contact. It's resistance. And so the table beneath your hand isn't truly touching you. It's pushing back, gently, invisibly, relentlessly. That push is all you'll ever feel. It's strange, isn't it? All the things we take for granted, the ground beneath us, the clothes we wear, the hug from a loved one, none of them involve actual atoms touching. They involve invisible forces, sensed and interpreted by a brain that evolved to treat those forces as reality. So tonight, we begin our journey with this realization, that the very first thing you think is true, that you're touching something, is already an illusion. A useful illusion, a necessary one, but an illusion all the same. And as we move forward, we'll uncover just how deep that illusion goes. You already know now that your hand never truly touches the table. But what exactly are your hand and the table made of? To understand why nothing ever connects, we need to look more closely at the smallest pieces of matter, atoms. Atoms were once thought to be the smallest building blocks of everything. The word itself comes from the Greek atomos, meaning indivisible. But science quickly proved the name wrong. Atoms are not solid marbles. They are more like systems, tiny solar systems, but stranger. At the heart of every atom is a nucleus. That's where you find the protons and neutrons, tightly packed together. Protons carry a positive charge. Neutrons, true to their name, are neutral. This nucleus is incredibly dense. If you could take a teaspoon of pure atomic nuclei, it would weigh billions of tons. But it's also tiny. If the whole atom were the size of a stadium, the nucleus would be a fly buzzing at the center. Surrounding this nucleus is the electron cloud, a wispy, dynamic, nearly ghost-like haze of negatively charged particles. But electrons don't orbit the nucleus like planets around a star. They behave more like waves than solid particles. Their position is not fixed. You can't point to a spot and say, that's where the electron is. Instead, you can only speak in probabilities. Physicists call this the electron's cloud, a mathematical blur of where the electron is likely to be found. That cloud defines the boundary of the atom, the part of it that resists others from coming too close. This means most of what we consider matter is, physically speaking, space. Empty space. Here's a strange thought. If you removed all the space inside the atoms of every human being on Earth, if you compressed all the nuclei together, you could fit the entire human race into the size of a sugar cube. Not metaphorically, literally. A sugar cube made of pure atomic nuclei would weigh trillions of kilograms. Now that's density. And yet, despite this emptiness, matter feels solid. The table doesn't collapse when you lean on it. Your body doesn't dissolve into vapor. Why? Because what holds it all together isn't the particles themselves. It's the forces between them. Electromagnetic force, strong nuclear force, weak nuclear force, gravity. In everyday life, the most important of these is the electromagnetic force. It's the one that makes atoms stick, that causes electrons to repel one another, that makes things feel solid when they are not. But the other forces play their roles too. The strong nuclear force is what holds protons and neutrons together in the nucleus. It's unimaginably powerful but only works at very short ranges, about the diameter of a proton. If it didn't exist, atoms would fly apart instantly. The weak nuclear force, though less famous, is essential in radioactive decay and in the nuclear fusion that powers stars. Gravity, curiously, is the weakest of all. Yes, it holds planets in orbit and pulls your body toward Earth. But at the scale of atoms, it's almost irrelevant. It's about 10 to the power of 36 times weaker than the electromagnetic force. Physicists still debate whether gravity can ever be fully unified with the other forces. It remains an outlier, a strange, stubborn wrinkle in our understanding of how the universe works. But back to atoms. Even the shape of an atom isn't straightforward. Atoms don't sit like static Lego bricks, neatly locked in place. They vibrate. They shift. They interact. Their electrons jump energy levels, sometimes absorbing or releasing photons, tiny packets of light. In fact, every color you see is due to electrons transitioning between levels, giving off light in the process. So when you look at a glowing object, you're seeing electrons in motion. Excited electrons falling to lower states and releasing energy. That's what makes a neon sign glow. That's what makes a sunset red. All of this, the structure of atoms, the behavior of electrons, the play of forces, is happening constantly, silently, everywhere. In your skin, in the chair you're sitting on, in the stars overhead. And yet, in all this busy structure, actual contact is nowhere to be found. Not even when atoms are packed tightly together in solids. Not even in the heart of a diamond. Every solid object is still a sea of space. Its particles are not touching. They are resisting. That resistance is enough to hold your weight, to stop your fall, to let you feel a surface beneath your fingertips. But it's still resistance, not contact. It's hard to grasp. Our senses deceive us constantly, but physics does not. So tonight, as you lie in bed and feel the mattress beneath you, remember, what you're feeling is the balance of forces, not a physical connection. Your atoms and the bed's atoms are keeping a respectful distance. And that distance, it's what keeps the world from collapsing. By now, we've established that atoms are mostly space, and that they never really touch. But what exactly stops them from doing so? The answer lies in one of the most fundamental rules of nature: the behavior of electrons, particularly how they arrange themselves in clouds, and how those clouds refuse to overlap. Imagine two people walking toward each other with umbrellas open. They get close, but the umbrellas bump before the people do. The umbrella fabric keeps them apart. Now imagine those umbrellas are made of energy fields. That's the electron cloud, a field of probabilities that surrounds every atom, keeping others at a safe distance. Electrons are peculiar little entities. They don't orbit the nucleus in the classical sense. They exist in orbital zones, regions where they are likely to be. These regions are shaped by the atom's energy levels and the quantum mechanical rules that govern particle behavior. When two atoms approach each other, their outer electron clouds begin to interact. But instead of overlapping, they push against each other. Why? Because electrons carry negative electric charge, and negative charges repel other negative charges. That's one of the oldest, most reliable rules in all of physics. Like charges repel, unlike charges attract. So, as your hand approaches the surface of a table, the outermost electrons of your skin come into range of the electrons in the table's atoms. These clouds don't wait until they are face-to-face to react. They start pushing away the moment their fields begin to overlap, even at a tiny distance apart. This pushback is the electromagnetic repulsion force, and it gets stronger the closer they get. Eventually, a balance is struck. You can't push any closer without applying more force than your muscles are willing or able to deliver. That limit becomes the illusion of contact. But in truth, there's still a tiny, invisible gap between the atoms in your skin and the atoms in the table. That's the electron cloud barrier. The reason you don't fall through walls or sink into chairs. Not because the particles are touching, but because they refuse to. Now here's where it gets even more interesting. Electrons, despite being particles, also behave like waves. This means their position isn't fixed. You can't point to one and say, there it is. Instead, you get a probability cloud, a fuzzy map of where the electron might be. This idea, rooted in Heisenberg's uncertainty principle, tells us that the more precisely you know where an electron is, the less precisely you can know how fast it's moving, and vice versa. Because of this, the electron cloud isn't a hard shell. It's a field of probabilities, and those fields interact long before the actual particles would bump into one another, if that were even possible, which is not under normal conditions. So when you think you're pressing your hand on something, you're really just pushing into a cloud of probabilities, a field that says, far enough, and sends a signal back to your nerves. There's something poetic in that. Our entire physical reality, the way we build chairs, climb stairs, hug people, is governed by invisible clouds of negative charge politely refusing entry. And yet, those same electrons are essential to everything that does happen. They define how atoms bond. They control electricity and chemical reactions. They give us light, heat, structure, and yes, even color. But when it comes to touch, they don't allow it. Even in solid objects, where atoms are tightly packed in orderly lattices, the electron clouds don't overlap. They stay in their lanes, like well-trained dancers on a crowded stage. They move, they vibrate, they exchange energy, but they never collapse into one another. Physicists still debate whether the electron cloud can ever truly be penetrated under normal circumstances. Right now, the answer appears to be no. The electromagnetic repulsion grows so strong at short distances that it overwhelms any force you're likely to apply. In fact, trying to force two atoms to touch would require pressures so immense that matter itself begins to behave differently, like in the heart of stars or neutron stars, which we'll get to later. But for now, just imagine the world around you for what it really is. A vast space of invisible repulsion zones. A kind of universal polite distance, where everything holds its shape not through contact, but through refusal. The table holds you up. The pen stays in your hand. Your feet don't fall through the floor. But it's not because any part of you touches anything else. It's because the electrons in your atoms are constantly saying, this far and no further. By now, you understand that at the smallest scale, the physical world doesn't operate like our senses would have us believe. But let's focus more closely on this strange force that gives rise to the sensation of touch, electromagnetic repulsion. When you hold a glass of water or type on your phone, you're not really in contact with these objects. Your atoms aren't fusing with theirs. What you're experiencing is a force, a silent, invisible pressure that arises from the electric charges in the atoms of your body and the atoms of everything else. Let's break this down. Every atom contains electrons, and those electrons carry negative charge. When two atoms get close, their outer electrons begin to repel each other, not because they are rude or shy, but because nature demands it. It's a fundamental rule. Negative charges resist overlap. This repulsion, when scaled up to billions of atoms across a surface, creates a strong, uniform pressure. That pressure is what holds you upright in a chair. It's what stops your hand from sinking through your keyboard. It's what makes a spoon rest in a bowl instead of falling straight through the ceramic. So when you feel an object pushing back against your skin, you're feeling the result of electromagnetic force fields interacting. It gets even more interesting when you realize that these forces act at a distance. The atoms in your fingertips don't need to collide with the atoms of your coffee mug to exert pressure on one another. They only need to get close enough for their fields to overlap. And that overlap happens at the scale of nanometers. Your body, in turn, has sensors designed to respond to that interaction. Specifically, the mechanoreceptors in your skin detect changes in pressure, vibration, and tension. They don't detect contact. They detect deformation, changes in skin shape caused by the resistance of outside objects. So even your sense of touch is based on interpretation. Your brain is making educated guesses based on input signals that come not from atoms meeting, but from fields pushing against each other. In a way, you live in a world that is constantly pushing back, not with hostility, but with structure. It's how things hold together. Without electromagnetic repulsion, matter would collapse into itself. Solids would behave like liquids, liquids like gas. And you wouldn't stay upright very long. This force is part of the electromagnetic interaction, one of the four known fundamental forces of nature, alongside gravity, the weak nuclear force, and the strong nuclear force. Of these, electromagnetism is by far the most dominant in your daily life. It governs electricity, magnetism, chemical bonds, the shape of molecules, and yes, the illusion of touch. Without it, no two objects would ever resist each other. Everything would simply fall into everything else. Buildings would collapse, stars wouldn't shine, and your body would disintegrate into a ghostly soup of collapsing particles. Physicists still debate whether this electromagnetic repulsion has a deeper unifying theory. Some think it could be explained through higher dimensional interactions or by merging it with the other forces under a single framework, a goal known as the grand unified theory. But for now, it's enough to know this. Everything you perceive as solid is the result of charged particles refusing to share space. Now, here's a fun twist. Even though the force is immensely strong at close range, it weakens with distance. That's why you can hold your hand near an object without feeling anything. But as you bring it closer, resistance rises. The fields begin to overlap, and suddenly, your nerves detect pressure. That precise balancing act is what defines the world of physical objects. The space between things, the not quite touching, is where everything happens. It also explains why objects don't pass through one another. When you throw a ball against a wall, the atoms of the ball and the atoms of the wall never merge. Instead, their electron fields repel one another so strongly that the ball bounces back. Every bounce, every step you take, every key you press, it's all electromagnetic repulsion at work. And this isn't just a human experience. Birds on a branch, bacteria in a drop of water, robots gripping metal. None of them are touching anything. They interacting through fields. Always close, never colliding. So tonight, as you settle in and feel the soft push of your blanket against your skin, remember, it's not the fibers you're feeling. It's the force they exert. An invisible, perfect pressure field shaped by charge. And that's what touch really is. Not contact, not collision, just repulsion, interpreted as comfort. By now, you've seen how electromagnetic repulsion keeps atoms apart, giving rise to what we perceive as touch. But there's another rule of nature that's just as important in maintaining this invisible boundary, the Pauli exclusion principle. At first glance, it doesn't sound dramatic. Two identical fermions can't occupy the same quantum state. Simple enough. But this principle, discovered by Austrian physicist Wolfgang Pauli in 1925, is one of the most essential laws that stops the universe from collapsing in on itself. Let's break it down. Electrons are a type of particle called fermions. That means they follow a very specific set of quantum rules. And the biggest one is this: no two identical fermions can exist in the same place, doing the same thing, at the same time. That means no two electrons in the same atom can share the same energy level, orbital position, and spin. They have to find their own spot in the atom's structure. This is why electron shells exist. Why atoms have distinct layers of electrons that build up as you move across the periodic table. This rule also applies when two atoms come close to each other. As the outer electrons of one atom approach those of another, they run into a problem. If they were to overlap, some of them would be forced into the same quantum state. But Pauli says no. So instead of merging, the atoms resist. That resistance adds another layer of repulsion, not just because of their electric charges, but because quantum physics simply forbids them from getting too cozy. It's not just about electricity. It's about identity. Electrons are like introverts at a party. They don't mind being in the same room, but they absolutely will not sit in the same chair or dance to the same beat. This principle is what keeps matter puffed up. Without it, electrons would all collapse into the lowest available energy level. Atoms would lose their structure, and matter would become impossibly dense. You, me, the chair you're sitting on, all of it would condense into something far smaller and much less recognizable. In fact, we see what happens when the Pauli exclusion principle is overwhelmed. In the heart of white dwarf stars, gravity is so strong that atoms are squeezed incredibly close together, but they don't collapse entirely. Why? Because the electrons refuse to share states. The result is electron degeneracy pressure, a direct consequence of Pauli's rule. It's this same degeneracy pressure that keeps white dwarfs from imploding, unless even more pressure is applied. In that case, gravity wins, electrons are crushed into protons, and the star collapses further into a neutron star. There, only neutrons remain, and even they obey their own version of the Pauli principle. So yes, the reason you don't fall through the floor isn't just electrical, it's quantum mechanical. The very structure of reality includes a baked-in refusal to overlap, a built-in social distancing. Physicists still debate how far this principle extends. Are there scenarios, maybe in black holes, or beyond the edge of current models, where particles might behave differently? Could exotic states of matter emerge if the rules bend? So far, every experiment agrees with Pauli. The rule holds, and thanks to it, every atom maintains its shape. Every object holds its form. Every table, every spoon, every planet resists collapse. So when you press your hand against something tonight, when you feel its firmness, what you're really feeling is this cosmic bureaucracy at work. A rule that says, no double occupancy, no exceptions. It's not just a scientific curiosity. It's a quiet miracle of order. And it's happening every second, all around you. Your bed, your bones, your blanket. They exist not because they're in contact with something else, but because they are structured by what they cannot do. Share too much space. So close your eyes now, and know this. Even the smallest particles are keeping respectful distance. And that's what keeps the world from falling apart. So far, we've explored how atoms don't touch, how electrons repel each other, and how quantum laws enforce that distance. But you still feel things, don't you? You feel the bed beneath you, the pull of a blanket, the smooth rim of a mug. These sensations feel real, grounded, immediate. But here's the twist. Your brain is not reporting physical contact. It's reporting force signals, processed and interpreted as touch. Let's dig into what's really happening. Your skin is packed with specialized nerve endings. Some are close to the surface, detecting the brush of fabric, the tickle of wind. Others are buried deeper, sensitive to firm pressure, temperature, vibration, even pain. Together, they form your somatosensory system, your body's personal intelligence network for navigating the physical world. But these nerve endings don't measure atoms colliding. They don't register molecular merging. They don't even care about whether something technically touched you. What they detect is mechanical deformation, tiny changes in the shape of your skin, caused by electromagnetic repulsion forces pushing back. You tap your finger on a desk. The outermost atoms in your fingertip get close, very close, to those in the desk. As the repelling electron clouds push against each other, your skin compresses ever so slightly. This mechanical pressure activates mechanoreceptors, nerve endings designed to respond to tension or stretch. Those receptors fire. They send electrical signals through your spinal cord to your brain's somatosensory cortex. And your brain, trained by millions of years of evolutionary repetition, says, touch. But that conclusion is a useful lie. You didn't actually touch the desk. Your body just reacted to resistance. This illusion isn't a bug. It's a feature. Evolution never needed us to understand quantum physics. It just needed us to respond appropriately to our environment. If a surface pushed back hard enough, your brain interpreted it as solid. If nothing pushed back, it concluded, empty space. And this goes deeper. Your nerves don't fire for actual contact. They fire for threshold force. That means they wait for the repulsion between atoms to create a big enough deformation in the skin to trip a signal. That signal travels as an action potential, a tiny voltage spike that hops down your nerves like a domino trail. By the time your brain receives it, the event has already happened. You're reacting slightly behind real time, but the system is fast enough to feel instantaneous. Different receptors provide different layers of this illusion. Some detect texture, others detect pressure or edge sharpness. Some are tuned to sustain touch, others fire only at the beginning or end of contact. Together, they generate a rich, synthetic feeling of interacting with the solid world. But again, the atoms never touch. Now, here's something stranger. If the brain stops receiving these signals, it starts inventing them. People who lose limbs often experience phantom limb syndrome, sensations, even pain, from body parts that no longer exist. Why? Because the brain's map of the body remains intact. It expects signals and fills in the gaps when they are missing. Similarly, if you sit still long enough, with no new tactile input, your sense of where your body ends and the world begins starts to blur. The boundaries feel less defined. That's your nervous system pulling back from sensory input. So, what we call touch is really a kind of real-time simulation, run by a brain that translates invisible atomic repulsion into usable physical feedback. Physicists still debate how deep this simulation goes. Is our conscious perception of the physical world a full sensory hallucination? Is touch, like color and sound, not a property of the object, but an interpretation by the observer? Some philosophers and cognitive scientists argue that reality, as we experience it, is entirely model-based. You don't sense the world, you sense your model of the world, constantly updated by sensory inputs. Which leads us to a wild but serious idea. You don't touch objects. You touch your brain's interpretation of force data, shaped by evolution and tuned for survival, not for truth. Even illusions like the rubber hand trick, where a person feels a fake hand being touched as if it were their own, show how flexible and easily fooled our sense of touch really is. Tonight, as you feel the pillow beneath your head, understand that what you're really feeling is a field of energy pushing back. Your skin deforms, your nerves fire, your brain says that's soft. But no part of you is actually making contact. And yet, the illusion is perfect. It keeps you safe. It lets you move through the world. It's touch without touching. Let's take a moment to look around. At your bedside table, the lamp, the glass of water, all of it feels dense, solid, heavy, even. And yet, nearly all of it, down to the core, is made of almost nothing. This isn't poetic exaggeration. It's physical fact. Solids, the most substantial state of matter in your everyday experience, are composed almost entirely of empty space. If you take any object, a brick, a spoon, a gold bar, and strip it down to its atomic components, what you find is staggering. More than 99.9999999% of it is empty. This is because the structure of an atom is mostly void. As we've said before, at the center of an atom lies its nucleus, a dense cluster of protons and neutrons. Surrounding this nucleus is a vast electron cloud. But vast here is relative. The size of the cloud compared to the nucleus is immense. If the nucleus were a marble at the center of a sports stadium, the electrons would be circling out near the furthest rows. Everything in between. Empty. So how do all these mostly empty atoms create something that resists your hand, holds its shape, and supports your weight? It's not because the atoms are packed tightly like sandbags. It's because the forces between them form a kind of structural illusion, a cooperative tension held in place by repulsion, by symmetry, by rules. In a solid, atoms are arranged in a repeating pattern, like a 3D lattice. Think of it like scaffolding built from invisible beams of energy. Those beams are created by the electromagnetic force, the same one we discussed earlier that keeps electron clouds from overlapping. When you push on a solid, you're really pushing on that lattice of resistance. The atoms in your hand get close to the atoms in the surface, and as they try to invade each other's personal space, repulsive forces intensify, pushing back with matching strength. The structure flexes, just a little, then pushes you away. It's a beautifully balanced illusion, and it scales up. You might think that compressing something like a steel beam would bring the atoms closer together. And yes, technically, you can compress them slightly. But remember, atoms don't touch. They already exist at the limit of closeness, balanced by those repelling electron clouds and by the Pauli exclusion principle. To compress a solid by even a few percent requires tremendous force. That's why hydraulic presses are so impressive. They force already resistant materials into smaller volumes, fighting against nature's built-in safeguards. But even in the most compressed materials found on Earth, the vast majority of their volume is still empty space. Now, here's a humbling comparison. Imagine shrinking the human body down until all that empty space in its atoms is removed. All the protons, neutrons, and electrons compressed to touch each other without their usual spacing. You'd be left with a speck smaller than a grain of sand. But it would weigh as much as you do now, because the mass doesn't come from the space. It comes from the particles themselves. This strange truth also explains why materials with low mass can still be remarkably strong. Think of carbon fiber or aerogels. They are mostly space, yet capable of withstanding tremendous stress. Physicists still debate whether there's a deeper layer beneath atoms, if quarks and leptons are the true building blocks, or if there are more fundamental particles yet to be discovered. Some theories, like string theory, propose that all particles are actually tiny vibrating strings of energy, and that what we call matter is just the resonance of those strings in different ways. If that's true, then everything's solid, your desk, your bones, the earth, is really made up of vibrations in a deeper, invisible field. But even with what we know now, the message is clear. Solidity is structure, not substance. What you feel when you knock on a wall or hold a book is the resistance of fields, not contact, not density in the way you imagine it. It's organized emptiness, resisting change. There's a kind of quiet beauty in that. That everything you depend on, gravity, ground, touch, is the result of forces dancing in the void. That all the weight you feel is held up by nothing, arranged perfectly to pretend otherwise. So tonight, as you feel your body resting on your bed, take comfort in the lie. The illusion of weight, the illusion of contact, the illusion of being held. Because while the atoms in your bed and the atoms in your back never actually meet, they do just enough to hold you steady. And sometimes, that's all we need. So far, we've talked a lot about empty space, the space inside atoms, the space between them, and how that emptiness is responsible for much of the structure we perceive as solid. But is that emptiness really empty? According to quantum physics, not even close. Let's venture into one of the stranger neighborhoods of modern science, the quantum vacuum, a place where nothing is never really nothing. An empty space is buzzing with invisible activity. This brings us to virtual particles, brief, flickering visitors that emerge from nothing, do their part, and disappear without ever being observed directly. They are not exactly real in the classical sense, but they influence everything around them, including you. To understand how this works, you need to first know that, in quantum field theory, every particle is an excitation in its own field. There's an electron field, a photon field, a quark field, and so on. These fields stretch through all of space, even the parts that appear empty. But quantum fields don't like to sit still. Even in a vacuum, where there are no actual particles around, these fields fluctuate. They jitter. They vibrate. These fluctuations can briefly create pairs of particles and antiparticles, like electrons and positrons, that pop into existence and vanish again so quickly that they are not directly detectable. These fleeting entities are called virtual particles. They don't violate energy conservation because they exist only for an unimaginably short time, allowed by the uncertainty principle, which states that a particle can borrow energy as long as it returns it quickly enough. And while they don't stick around, their presence has consequences. For example, they influence the strength of the electromagnetic force. When two charged particles get close, like the electrons in your hand and the electrons in the table, virtual particles swarm between them. They slightly modify the force, changing how those particles repel each other. This is part of what gives the vacuum its surprising substance. It's not an empty backdrop. It's an active participant. And yes, this weird sea of virtual particles is part of what defines the gap between atoms. That tiny sliver of distance that keeps things from touching. It's not truly empty. It's a stage where invisible, momentary interactions are constantly playing out. Like tiny whispers exchanged between particles, reinforcing the no-entry policy of the atomic world. Virtual particles are also responsible for one of the most precise predictions in physics, the Lamb shift, a subtle change in the energy levels of hydrogen atoms, caused by interactions with these fluctuating fields. It was predicted theoretically, measured experimentally, and helped confirm that the vacuum is far from void. They also contribute to Hawking radiation, the theoretical process by which black holes could slowly evaporate. At the edge of a black hole's event horizon, a pair of virtual particles might pop into existence. One falls in, the other escapes, becoming real and carrying energy away. This strange idea suggests that black holes aren't forever. They could slowly shrink, dissolve, and vanish over time. Physicists still debate whether virtual particles are real or just mathematical artifacts. Some argue they're convenient placeholders, bookkeeping tools in quantum equations. Others believe they represent a deeper truth. that the vacuum itself has structure and agency. And if that's the case, then the space between your fingers and your phone, the invisible zone where your atoms stop and the phones begin, is filled with a kind of quantum foam. Tiny pulses of potential, shaping forces you don't see, but that guide your every interaction. So tonight, when you feel something solid, try to remember, the space between you and the object is alive, not with matter, but with momentary events, invisible flickers that enforce the rules of separation. In a way, you're surrounded by ghosts, not the spooky kind, but the mathematical ones, the unseeable, unmeasurable sparks that hold the fabric of reality together. Touch is not blocked by a wall. It's blocked by rules enforced by temporary bursts of possibility. The emptiness is doing more than you think. And that's one of the quietest wonders of all. Even nothing is something. So far, everything has been about distance, rules that keep atoms apart, forces that prevent true contact. But nature, being what it is, occasionally allows a rule to bend. Welcome to the strange and slightly rebellious world of quantum tunneling, a phenomenon where particles sometimes do what they absolutely shouldn't be able to do. In the classical world, barriers are absolute. A ball won't pass through a wall. A car can't phase through traffic. Even a grain of sand won't slide through a glass tabletop. But in the quantum world, these barriers are more like strong suggestions than laws. Quantum tunneling is a phenomenon where a particle has a small but non-zero chance of appearing on the other side of an energy barrier it doesn't have enough energy to climb over. It's like a marble rolling up a hill that's taller than the energy it has, and still somehow ending up on the other side without ever going over the top. This happens because, in quantum mechanics, particles like electrons aren't really little balls. They are wave functions. A particle isn't in one place. It's described by a spread-out probability cloud. And if that cloud overlaps with a forbidden zone, like the other side of a wall, there's a chance, however small, that the particle will be detected there. It didn't jump the barrier. It didn't go through in any classical sense. It was never entirely excluded from that region in the first place. So what does this have to do with touch? Well, if electrons can tunnel through barriers, you might wonder, can atoms tunnel through each other? Can a person just phase through a wall? Or a hand pass through a solid surface? Theoretically, yes. Practically, no. The probability of a large object, something composed of trillions of particles, quantum tunneling through anything is so minuscule that you need to wait longer than the age of the universe for it to happen once. And even that would be optimistic. In reality, tunneling is only relevant at the scale of individual particles, and even then only under special conditions. But it's not just a theoretical trick, it has real-world consequences. For example, tunneling is essential in nuclear fusion, the process that powers the sun. Inside the sun, temperatures are high, but not quite high enough for protons to overcome their natural repulsion through brute force alone. Instead, they tunnel through the energy barrier, allowing fusion to occur and sunlight to eventually reach Earth. Tunneling is also the key to semiconductors and quantum computing. Devices like tunnel diodes and quantum dots rely on particles slipping through barriers in predictable, engineered ways. It's even used in scanning tunneling microscopes, where a fine metal tip is brought so close to a surface that electrons can tunnel between them. This allows scientists to map individual atoms, getting closer to matter than any camera ever could. Still, as astonishing as tunneling is, it doesn't break the no-touch rule. It doesn't allow atoms to collapse into one another, or electrons to ignore their mutual repulsion en masse. It's more like a quantum cheat code, only usable under the right conditions, and with microscopic players. Physicists still debate the nature of tunneling. Is it truly instantaneous? Does the particle travel through the barrier, or simply appear elsewhere? Experiments show that tunneling may happen with no measurable time delay, leading to bizarre questions about causality and the flow of time itself. There's also ongoing research into macroscopic quantum tunneling, the idea that under certain extreme conditions, collections of particles might tunnel as a group. It's still speculative, but if true, it would open doors, or phase through them, that we never thought possible. So why include tunneling in a story about touch? Because it reminds us that even in a universe governed by repulsion and separation, there are rare, fleeting exceptions. Tiny rebellions against the rules that say, "You can't be here." And the particles respond, maybe just for a moment. Even if it doesn't let you walk through walls, it does let the sun shine. It lets electronics function. It lets matter change forms in ways that brute force never could. Tonight, as you drift off, consider this. There are rules that hold the world together. But at the smallest scales, even rules can flicker. And in that flicker, particles pass through what should be impossible. Quietly, instantly, like a ghost whispering. Why not? For all we've said about electrons repelling, particles keeping their distance, and atoms being mostly empty space, there's a place in the universe where this rule breaks down. Where atoms don't just resist each other, they collapse into each other. And in doing so, they create one of the strangest and most extreme objects ever discovered, the neutron star. Let's rewind. Imagine a star much more massive than our sun. It lives out its life burning hydrogen, fusing atoms in its core, generating incredible amounts of energy. But that fuel eventually runs out. The star cools. Gravity, once held in check by the outward push of fusion, takes over. The core collapses, catastrophically. Under ordinary conditions, the electrons around atoms repel each other. They keep their distance. They obey the Pauli exclusion principle. But in the heart of a dying massive star, gravity applies a different kind of pressure. A crushing, overwhelming force that doesn't care about personal space. Electrons are squeezed into the protons inside atomic nuclei. And when that happens, something strange occurs. They combine to form neutrons. This reaction turns the entire core into a kind of gigantic atomic mash. One massive ball of neutrons. No electron clouds. No electron repulsion. Just densely packed, bare neutrons, shoulder to shoulder. Hey, finally, matter does what it's never allowed to do anywhere else. It touches itself. What you're left with is a neutron star, an object so dense, a single teaspoon of it would weigh billions of tons, the size of a city, but heavier than the sun. Its gravity is intense enough to bend light, warp time, and pull atoms apart. And the space inside it? Practically none. The atomic structure we've spent 9 sections talking about. Gone. No orbitals. No clouds. No distance. Just neutrons. As close as the laws of physics will allow them to be. Even here, however, something resists total collapse. The neutron degeneracy pressure, a sibling of the electron degeneracy pressure we mentioned earlier, kicks in. Neutrons, like electrons, are fermions. And fermions hate sharing quantum states. So even in this most extreme of environments, there's still a force saying, no closer than this. Even at the threshold of physics, nature maintains a kind of last resort boundary. Still, it's as close to true atomic touch as the universe gets. No space between nuclei. No polite repulsion. Just pure compression. Physicists still debate what lies inside neutron stars. Are they pure neutron soup? Do stranger states of matter exist at the core? Some theories propose quark-gluon plasma, a kind of breakdown where even neutrons disintegrate into their fundamental parts. Others speculate about strange matter, hypothetical particles that might be even more compact than neutrons. And then there's the final step. If a neutron star gains even more mass, perhaps by absorbing material from a companion star, it can collapse further, becoming a black hole. At that point, even the degeneracy pressure gives up. Matter is crushed to a point of infinite density, a singularity. There, all bets are off. We don't know what happens inside a black hole. Physics stops being predictive. Some scientists think everything is compressed into an infinitely small point. Others believe it may form a new kind of structure beyond our understanding. Maybe space and time themselves bend into something unrecognizable. But we do know this. Before things reach that point, neutron stars give us a glimpse of what happens when the universe lets go of all the repulsion. When atoms stop keeping their distance. When the rules that keep your hand from sinking through a table are finally overruled. In neutron stars, the illusion of touch becomes something else, a collision of identity. No more space between particles, just raw existence, compressed and humming in the dark. So tonight, as you lie in your bed, resting gently atop invisible repulsion fields, know this. You're lucky the atoms hold back, because when they don't, the result is terrifying. Let's take a step back from collapsed stars and return to something a little more familiar. Your everyday existence on Earth. You walk across the floor. You sit on a chair. You lean against a wall. And not once do you fall through. Given everything we've discussed so far, that atoms never touch, that everything is mostly empty space, you might reasonably ask, why not? Why doesn't your body pass through solid objects if it's made of particles that never actually make contact? The answer, as strange as it sounds, is still forces. Not substance, not density, but invisible interactions that push back just enough. When you stand on the floor, the atoms in your feet are hovering ever so slightly above the atoms in the floorboards. Their respective electron clouds never overlap. Instead, as the distance between them shrinks, the electromagnetic repulsion intensifies. That repulsion increases until it perfectly cancels out the force of gravity trying to pull you down. In other words, you float, by an absurdly tiny distance, on a cushion of electromagnetic force. It's like trying to bring two powerful magnets together the wrong way. As they get closer, the resistance grows so strong that no matter how much harder you push, you just can't make them touch. The closer they get, the harder they push back. Now multiply that by billions of atoms across every square inch of your body. That's why you don't fall through the floor. That's why your bed doesn't sag into the Earth's core. Because at every microscopic point of contact, the repulsion between particles reaches equilibrium with the downward pull of gravity. This balance point is what we casually refer to as standing. Even now, your entire body is resting on this delicate balance, one of nature's most dependable feedback loops. You push down, the world pushes up, but neither side makes contact. It's all negotiated at the atomic level, with the strong but invisible hand of electromagnetism. It's worth noting that, in terms of sheer strength, the electromagnetic force is about 10 to the power of 36 times stronger than gravity. That's a 1 followed by 36 zeros. In comparison, gravity is almost laughably weak. It takes the combined mass of an entire planet to hold you down, while the electromagnetic fields in a handful of atoms can keep you from falling through a wooden floorboard. This is one of the more overlooked mysteries in physics. Why is gravity so weak? Physicists still debate whether gravity is diluted across extra dimensions or whether it operates under principles we don't yet fully understand. Some theories suggest that gravity's weakness is an illusion caused by the way it interacts with high-dimensional space, a concept from string theory. Others believe gravity might be a fundamentally emergent force, not a primary one. But despite its weakness, gravity is persistent. It never shuts off. It affects all mass equally. So even though it's outgunned by electromagnetic repulsion at the atomic level, it remains the reason you have weight. Still, it's not gravity that keeps your atoms apart. It's a refusal of electrons to share space, combined with that quantum rule we discussed earlier, the Pauli exclusion principle. Together, these forces build a world of seeming solidity, a world where you can sit, stand, lie down, and rest, without ever once actually making contact with anything beneath you. And yet, your body knows how to respond. Your nerves detect the rising pressure as your body nears a surface. They send signals to your brain. Your brain interprets those signals as support, comfort, or firmness. So even though you're floating, at the tiniest scale imaginable, it feels like you're held. It's worth pausing here, because this is one of those quiet truths that rewires your understanding of the physical world. You've never truly touched the ground. Not when you walked barefoot in the grass. Not when you sprawled out on the beach. Not even when you fell off your bike and landed on the pavement. Every interaction has been force-based. Every collision has been an illusion of contact. But the illusion works. It holds you up. It guides your balance. It lets you build homes and bridges and highways. All thanks to atoms that resist but never embrace. So tonight, as you lie in your bed and gravity gently tugs on your body, remember, what's holding you up isn't a hard surface. It's a quiet standoff between two invisible armies of electrons, neither side willing to give ground. And in that standoff, you find rest. Now that you know humans never really touch anything, here's a fun twist. Neither do bacteria. Even at the microscopic scale, where things are unimaginably small, where cells and molecules bump up against each other all the time, touch still doesn't happen the way we think it does. Let's imagine a single bacterium drifting through a drop of water. It's a simple organism, with a soft, flexible membrane and a few strands of genetic material inside. It wiggles using tiny hair-like structures called flagella. It searches for food, avoids danger, and divides when the time is right. At this size, the world is a soup of forces. Fluid dynamics behave differently. Water feels thick, almost like syrup. Every molecule in that drop of water is bouncing, pushing, jostling, constantly in motion. But none of them, not even one, touches the bacterium in the strict atomic sense. When a bacterium collides with another, what's actually happening is this. Their electron clouds begin to repel each other. Just like with you and a table, just like with magnets that won't meet. The repulsion becomes too great, and the two surfaces deform, or shift, or change behavior, but never overlap. Even when bacteria sense their environment, detecting chemicals, temperatures, or surfaces, they do so without direct atomic contact. They rely on molecular receptors embedded in their membranes. These receptors detect changes in concentration gradients or respond to chemical binding events, both of which are governed by electromagnetic interactions, not by atoms merging. Even during processes that seem incredibly intimate, like bacterial conjugation, where two bacteria connect to exchange genetic material, there's still a microscopic buffer zone maintained by physical laws. Structures like pili extend from one bacterium to another, creating what appears to be a physical bridge. But zoom in far enough, and once again, you're dealing with forces, not actual touch. Let's go smaller. Viruses, for example, don't touch the cells they infect. They dock with surface receptors on a host cell, triggering a series of chemical and mechanical interactions that allow the viral genetic material to enter. But even then, no atoms touch. It's all about fitting shapes, charge distributions, and probabilities. The illusion of touch even governs immune responses. White blood cells don't tackle invaders through brute contact. They recognize foreign proteins, latch on through molecular keys and locks, and trigger responses via cascading molecular signals. Every step of that process, binding, recognition, attack, is conducted via proximity and force interactions, not physical contact. The world of the small is governed by the same rules as the world of the large, just with less room for error and more consequences for small changes. What makes this even more fascinating is that life itself thrives on near misses. Enzymes catalyze reactions not by smashing molecules together, but by gently aligning them, guiding electrons with precision to encourage bonds to form or break. Proteins fold into elaborate shapes not through pressure or impact, but through an exquisite balance of forces: hydrogen bonding, van der Waals forces, hydrophobic effects, all of which involve no actual touching. Physicists still debate the role of quantum effects in biological systems. There's evidence that quantum tunneling plays a role in some enzyme actions. Some researchers even suggest that photosynthesis operates with surprising quantum efficiency. In each of these cases, though, the pattern holds. Atoms and molecules interact without physically colliding. So when we say touch in biology, we're really talking about binding, repulsion, or chemical reaction, all of which happen due to fields, not contact. And this applies all the way down to DNA. When two strands of DNA zip together, it's not because they've crashed into each other. It's because their shapes and charges align in just the right way. The bases match up, and the fields stabilize long enough to hold them in place. Even at the heart of heredity, even in the code of life itself, nothing truly touches. So tonight, as you picture the teeming microcosmos inside your body, your skin, your gut, your bloodstream, know that none of those cells are actually in contact with anything around them. Not your immune cells, not your neurons, not even the bacteria living on your skin. Everything is suspended in a sea of electromagnetic negotiations. No meetings, just close approaches. No touch, just agreement. The entire biological world exists because atoms respect invisible boundaries. And somehow, life thrives in the gap. So far, we've covered how touch is an illusion, built on atomic repulsion and quantum rules. But some things feel especially solid or sticky. Glass, glue, wet skin, even the surface of water. If everything avoids actual contact, what makes some materials seem like they cling, stretch, or resist more than others? Let's talk about sticky forces. Those subtle interactions that still don't involve atoms touching, yet create the sense of cling, drag, and tension. Take surface tension, for example. You've probably seen it in action. A drop of water perched perfectly on a leaf, a needle floating on water despite being denser than it, or a mosquito walking across a pond like it's a trampoline. All of these strange behaviors are thanks to cohesive forces between water molecules. Forces that, once again, arise not from contact, but from electromagnetic interactions between atoms that never meet. Water molecules are polar. That means each molecule has a slight positive end and a slight negative end. The oxygen atom hoards electrons, while the hydrogen atoms share them reluctantly. As a result, water molecules behave like tiny magnets, each one tugging at its neighbors through what's called hydrogen bonding. These bonds are weak compared to the covalent bonds that hold atoms together, but strong enough to make water unusually sticky compared to other liquids. At the surface, there are fewer molecules for a water droplet to cling to, so those on the edge are pulled more tightly inward. This creates the effect of a kind of elastic skin across the water's surface tension. Still, no atoms actually touch. The molecules stick together only because of force fields between their electrons. You can distort this balance, push against it, break it, but never fully collapse it. The same principle is at work when adhesives bind two surfaces together. Glue doesn't work because it worms its way between atoms and knits them together. It works because its molecules form strong electromagnetic interactions with the surfaces it's applied to. Van der Waals forces, hydrogen bonds, sometimes even ionic or covalent linkages depending on the formulation. In essence, glue is a clever molecular diplomat. It bonds strongly with both sides, clinging through force fields rather than direct contact. Even friction, the thing that stops your hand from sliding off a doorknob, doesn't come from atomic grip. It comes from the interlocking geometry of surface bumps, amplified by molecular attraction. At the microscopic scale, every surface is rough, filled with peaks and valleys. When two objects rub against each other, their highest points meet, as closely as repulsion will allow, creating resisting forces at each contact site. But those resistances, still governed by electron repulsion, no atoms grinding together, just forces pushing back. The stronger the electromagnetic interactions at those points, the more sticky the surface feels. That's why your hand feels different on polished glass than it does on rough concrete. The difference isn't in how much the atoms touch, but in how strongly the molecules interact at those few near-contact zones. You may have noticed this effect in reverse on a rainy day. When water gets between your shoes and the floor, it reduces friction. The water molecules form a barrier, replacing high-friction solid-solid interactions with low-friction liquid-solid ones. It feels slippery, but again, no one's touching. It's just that the repulsive fields are being managed differently. Physicists still debate the full nature of friction. Is it entirely electromagnetic? Are there quantum contributions? Do phonons, vibrational energy packets, play a role in energy loss? Some experiments suggest that even Casimir forces, those tiny forces arising from vacuum energy fluctuations, might influence how surfaces interact at ultra-small scales. What's clear is that sticky isn't about contact. It's about energy exchange between fields, forces trying to find a balance, and in doing so, creating temporary resistance. Even something as strange as gecko feet, which can cling to glass or walk upside down, operates through van der Waals forces. Their tiny foot hairs make such close contact with surfaces that the electromagnetic interactions become strong enough to hold their entire body weight. But, as always, no atom touches another. The gecko clings by floating incredibly close. So close the illusion becomes physically useful. So next time you peel off a sticker, feel honey stick to your fingers, or notice how a drop of water clings to your window. Remember, it's not about contact. It's a carefully choreographed interaction of fields, charges, and force balances. Your brain feels stickiness, but your atoms never connect. Not even a little. At this point, we've dismantled something deeply intuitive, the belief that touching is real, that there's direct connection between your hand and the world. You've learned that atoms never actually touch, that your body rests on invisible repulsion fields, and that even the stickiest, closest, most intimate interactions happen across gaps maintained by force. It's not a failure of sensation, it's a triumph of illusion. But what does that mean? Because this isn't just physics. It's something more unsettling, something philosophical. You have never truly made contact with anything in your life. Not the skin of a loved one, not the soil beneath your feet, not the objects you've built, broken, or held in joy or grief. This distance, the microscopic barrier that never goes away, is everywhere. And yet, our entire emotional world is built on the idea that it doesn't exist. When a parent cradles their newborn, when two friends shake hands, when lovers embrace, there's a belief, an unquestioned feeling, that something real, physical, and mutual is happening, that some kind of boundary has been crossed. That touch confirms the world is shared, present, and warm. But physically, nothing meets. No atoms connect. The body stays separate, floating close, pushing back, but never merging. Your skin does not touch the world. It senses resistance, and your brain calls that presence. This raises a deeper question. Are we ever truly in contact with the universe? Or is every experience a filtered version, translated by nerves, processed by brain cells, dressed up in illusion to make the world manageable? Philosophers have circled this for centuries. Descartes, Hume, Kant, they all struggled with the limits of perception. What is real? What is experience? What lies behind the screen of sensation? Modern science has only sharpened the question. We now know that vision, hearing, taste, touch, they are all interpretations of physical phenomena. You don't see light. You perceive how your brain reacts to it. You don't hear sound. You feel pressure changes in the air. And you don't touch an object. You register the boundary where its electrons push back against yours. This isn't to say reality is fake, just that it's experienced through layers. Layers you didn't design. Layers you can't remove. And while you live in a world made of atoms, you don't experience those atoms directly. You experience fields, reactions, and probabilities. You live inside a model that your brain constantly updates, a reality assembled from guesses, signals, and ancient survival needs. Physicists still debate the nature of this boundary. Is the real world knowable at all? Some argue that quantum mechanics proves reality is inherently probabilistic. Others say that what we call observation collapses possibility into a single outcome, that our perception might shape reality itself. And then there's the simulation hypothesis, the idea that everything you experience is part of some programmed system, and that sensation, including touch, is just data fed into your consciousness. In that framework, atoms aren't even real. They're code, and distance is a variable defined by someone else's parameters. But you don't have to go that far to feel disoriented. It's enough to recognize that the very thing that makes the world feel grounded, the sense of physical contact, is constructed. A useful lie, a biological agreement with physics that says, close enough is close enough. And if you follow that line of thought, it gets even stranger. You are never physically connected to anything. But emotionally, psychologically, you're deeply entangled. You feel connected. You believe in contact. And that belief shapes everything. Your relationships, your memories, your sense of belonging. We say things like keep in touch, it touched my heart, or they reached out. These metaphors are built on a sense of connection we never physically achieve. But they work. Because while atoms may never merge, meaning does. And meaning doesn't require contact. So tonight, if this idea leaves you feeling a little lonely, remember this. Everyone else is floating too. No one truly touches. And yet, we still connect. Through voice, gesture, thought. Through shared illusions that help us survive. We might not meet at the atomic level, but that hasn't stopped us from finding closeness in every other way. So if the world is built on distance, so be it. We've learned to find comfort in the space between. Let's return now to where we began. With the simple act of pressing your hand on a table, you now know there's no real contact. That what you're feeling is the subtle repulsion of particles that refuse to let each other in. That your entire body floats on fields, never once making true contact with the world around it. But the real wonder is this. You are still held. You're held by rules, by resistance, by something that isn't substance, but structure. You walk, sleep, build, and touch in a world that resists without colliding. And that resistance, that empty space behaving as if it's full, is what gives form to everything you know. Even now, as you rest, you're suspended above your mattress by a vast network of repulsive forces, too small to see but strong enough to carry your weight. The atoms in your body push back against the atoms below you, not with violence, but with patient insistence. And the bed agrees. It holds. It lifts. It supports. And in that invisible handshake of force fields, you find comfort. That's the strange piece of reality. It holds you without holding you. It gives you something to stand on without offering you anything solid. It surrounds you with form, even though most of it is nothing. This illusion is not a failure of physics. It's a feature. A delicate balance between the laws of energy, charge, and probability. The same laws that hold up bridges and mountains are the ones that make your pillow feel soft tonight. And you don't need to touch the world to be part of it. Because what we call touch is just a language of proximity, force, and feedback. It doesn't require atoms to merge, only to communicate. And they do. Constantly, quietly, relentlessly. Physicists still debate how deep this goes. Whether the universe is made of particles, or fields, or information. Whether space and time are fundamental, or just emergent properties of something more abstract. But one thing seems certain. Distance is not emptiness. It is relationship. It is order. It is the invisible scaffolding of existence. And in that space between things, everything you know is built. So, as you lie still, cushioned by forces you cannot feel directly, let this idea settle in. You are part of a world where nothing touches, but everything holds. Where distance does not mean disconnection, and where even the emptiest space is full of meaning. Now, let's slow down. Let your breath soften. Let your eyes drift heavier with each blink. You're not falling. You're being held. Let go of trying to grasp the world tonight, because even your atoms know nothing really grips. Instead, everything balances, just enough to stay. The floor doesn't catch you. It rises just before you fall. The mattress doesn't cradle you. It simply refuses to yield. And in this quiet agreement between particles, you find safety. All day long, your body has been moving through space it never touches. Yet here you are, safe, still, supported. The distances between atoms are unimaginably small, but within them, entire lives unfold. Within them, a whisper of resistance that means, here I am. And now, let your thoughts stretch out. Give them space, like atoms in a cloud. Let them rise, fade, return. With no pressure, no weight, no need to hold. Let the gaps between moments grow wider. Let the silence between thoughts linger a little longer. Nothing has to touch. Not now. Not tonight. Still, the world holds you. Without hands. Without contact. Without needing to prove anything at all. You're not falling. You're floating in certainty. And everything, absolutely everything, is exactly where it should be.